Well, this has certainly been an interesting week. I don't recall that UK has ever closed for this many days in a single week, or for this many days in a single semester. So this is going to be the material that we're going to cover in class on Thursday. As always, please let me know if you have questions. The best thing to do is going to be posting them on Piazza. I will be monitoring that throughout the weekend and answering questions as I am able. So what we want to look at now is intermolecular forces. And this kind of comes from what we talked about in class on Wednesday, talking about polar versus nonpolar, because what that allows us to do is once we know what type of molecule it is, it helps us see what types of intermolecular forces or intermolecular attractions that are happening between molecules. We've talked about bonds, which is that attractions, those forces that are holding atoms together. But now we're saying, well, what if I have two molecules, say of water? What's holding one water molecule next to the other water molecule? What kind of attractions are happening there? And the main thing that we look at for those kind of intermolecular attractions or intermolecular forces are charges. And these can be full charges, so positive and negative from a cation and an anion. These can be partial charges that we saw in our polar bonds, where we saw the partial positive and the partial negative, depending on which atom was more electronegative, the more selfish atom. Or we can see temporary charges. So even in non-polar molecules, we can actually get temporary charges where we have a temporary distribution of charge, even in nonpolar substances. Now, these are typically weaker than bonding forces. When we look at some very large molecules and kind of the cumulative amount of those intermolecular forces can become quite strong. But when we're looking at just like a single attractive force, it's always going to be weaker than any single bond. So here's a list of the types of forces we're going to talk about, as well as what kind of molecules they're found in. I would encourage you to pause here and write this down so you have this to refer back to as we go through the rest of the video. So what we're looking at are several types of intermolecular forces. The weakest of all of these are London dispersion forces, and you'll hear these called London dispersion, London, or dispersion forces. Any of those three names all really mean the exact same thing. And those London dispersion forces happen when we get those temporary charges. So this is when we have a temp charge. And so imagine that you're on, say, a whale watching expedition, and you're out on the boat and suddenly says, see, look, a whale. And what does everybody do? They run to the side of the boat, and temporarily the boat is tilted just a little bit, not too much, we don't want to end up in the water, but tilted just a little bit. Everybody looks and oohs and ahs at the whale goes away, and gradually everybody kind of migrates back and spreads out around the boat, and that little tip of the boat from everybody being on one side is now gone. So that was a temporary uneven distribution of people on the boat, and we can see the same thing in molecules. We can have a temporary uneven distribution of electrons, and from that we get this very small, very small positive and negative charge. Just like our partial charge we see in polar molecules, we see what we call a temporary dipole, or that partial charge that's just enough so that it can influence a molecule next to it. So if we have a little bitty negative charge on one molecule, then it's going to be influencing the molecule next to it, and so that molecule will have a little bitty positive charge, and so on and so forth. So that's a temporary charge. Next, we'll look at dipole-dipole forces, and this happens in our polar molecules, so between two polar molecules. And so what happens is we have a positively charged end and a negatively charged end. It doesn't matter that they're not full charges, it's still that partial positive, and it's going to be attracted to the partial negative of a neighbor molecule. So just like we would expect pluses and minuses to kind of line up and orient with respect to one another, we see the same thing happening with those partial charges, with those polar molecules. Next, we want to look at hydrogen bonding. And the thing we need to point out first is, one, it doesn't involve just hydrogens, and two, it's not really a bond, it's an intermolecular attraction. So the name for this is really bad, but that's what it is, and so we got to use it. But what we want to look at is what's going on here. And hydrogen bonding, which is generally stronger than dipole-dipole forces, which are generally stronger than London dispersion forces, but hydrogen bonding is a type of dipole forces. Okay? So it's kind of a fancy dipole force. And we can actually call this hydrogen Fon bonding, just as a way to help us remember what's actually involved when we're looking at a molecule that has hydrogen bonding. And what we see is that we have a hydrogen, so say let's look at C3OH. We have a hydrogen attached to a fluorine, oxygen, or nitrogen that is attracted to the fluorine, oxygen, or nitrogen on a neighboring molecule. So say I also have another methanol. This is a methanol molecule. So say we have another methanol molecule over here. What I'm going to see is an attraction between this hydrogen, which is attached to an oxygen, but it's attracted to the oxygen on a neighboring molecule. And so what we see here in the middle, what's in this dashed line, that's actually our hydrogen bond. Not really a bond, just an attractive force. But we have to meet this very specific definition of a hydrogen attached to a fluorine, oxygen, or nitrogen, and attracted to the fluorine, oxygen, or nitrogen on a neighboring molecule. And it goes back to those differences in electronegativity that we talked about, is that fluorine, oxygen, and nitrogen are really electronegative, and so they're really kind of stealing that electron density away from the hydrogen. And so as a result of that, we get a little bit more of a partial positive and partial negative than when we would get in a lot of other polar molecules. And so that's why we kind of categorize these a little bit different. We would still consider this molecule to have dipole-dipole forces. It just also has hydrogen bonding. Now I'm going to skip over the ion dipole for just a second until we talk about the ionic forces. Now the way we've talked about ionic forces already has actually been as ionic bonds. And so when you think about it, there's really not a sharing of electrons like we see in a covalent bond that's holding those atoms together. It's really a force, because say in sodium chloride, we have a positively charged species that's being held to that negatively charged species, and it's an attractive force. It's an electrostatic force between the opposite charges. And so ionic forces are also known as ionic bonds, and they're very strong, as we know, and we see these only in ionic compounds. So when I look at something like methanol, it's not going to have ionic forces because it doesn't have any ions. So now what I want to go back to is the ion dipole forces. And when I look at this, what I notice is that I've got two things here. I've got ion and I've got dipole. And this is a clue that when we have ion dipole forces, we actually have to have two things in our mixture. If I just have one substance, so just methanol, just water, just sodium chloride, any one substance, I can't actually have ion dipole forces. I have to have two things mixed together. And like the name suggests, one of those things must be an ion. It can be a cation or an anion. And the other thing must be a polar molecule. And so a prime example of this is when I look at something like sodium in water, and when I look at sodium in water, I have this partial positive. Well, if I look at water molecules, what I see is I get this partial negative on the oxygen side and a partial positive on the hydrogen side. And so where I see that intermolecular attraction is between the sodium ion and the oxygen. And in reality, we actually see several water molecules kind of surrounding that sodium ion. I'm not going to draw them all there because I don't have enough room, but here's what we're looking at for ion dipole. So we have to have two substances present. Now when we look at all of our intermolecular forces, we could have two substances present. We can talk about dipole-dipole forces between two different polar molecules, like we talked about the like dissolves like. Well, that's what's going on. But we don't have to have two. When we look at ion dipole forces, we must have two things present. So all of them we can, ion dipole we must. So let's look at an example here. We just have an alkane. So all we have are carbons. So 1, 2, 3, 4, 5 carbons. We'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens, so C5H12. There are no oxygens, there's no nitrogens, nothing in here to really add any polarity to the molecule. And remember that that carbon-hydrogen bond has a difference in electronegativity of about 0.4, so that's really on that cutoff between polar and nonpolar anyway. But because everything is very symmetrical and there's nothing else in the molecule, what we find is that this is actually a non-polar molecule. So it's actually not going to have any polarity to it at all. And when we're looking at it in terms of the dispersion for or the intermolecular forces, we start first with our dispersion forces. So we say, well, okay, it's London dispersion forces. It's a nonpolar molecule, so it will have those dispersion forces. And in fact, every molecule will have dispersion forces because the only thing we need to have dispersion forces are electrons. And every element, every molecule, everything has electrons in it, so we are always going to have dispersion forces. For a nonpolar molecule, these are the only types of intermolecular forces we're going to have are dispersion forces. So once I've determined nonpolar dispersion forces, and I'm done. I don't have to look at anything else. Now a little more complicated example here. We're looking at propanol. We've got 3 carbons there in our alcohol group at the end. So this is an alcohol molecule. Because I see this O in here, that's a big clue that I'm dealing with a polar molecule. Okay, so whenever I see oxygen, nitrogen, sulfur, fluorine, any of these guys is a big clue that we're dealing with a polar molecule. So what I want to do is I'm going to go through that list of the different types of intermolecular forces we can see and see which ones are actually happening in this particular molecule. Now we know that we're going to have dispersion forces because everybody gets dispersion forces. Nobody's left out of that because everybody's got electrons. So we all have dispersion forces, or all our molecules do. Next, I'm going to look at this and say, okay, it is a polar molecule, so that means I have dipole-dipole forces. So I have that partial negative, partial positive attraction going on. I also see that I'm going to have hydrogen bonding because I meet my definition here. I have a hydrogen attached to a fluorine, oxygen, or nitrogen, and it's going to be attracted to the fluorine, oxygen, or nitrogen on a neighboring molecule. So let me show you what I mean here. Let's draw out another propanol molecule. So if we have OH, okay, so if we have this propanol molecule, what we see is we're going to have an attraction between our hydrogen here and our oxygen there. Now this hydrogen could be attracted to another oxygen and so on and so forth, and there could be a hydrogen attracted here. All these different things, ways these molecules can interact with one another. But the key definition here, hydrogen attached to a fluorine, oxygen, or nitrogen and attracted to the fluorine, oxygen, or nitrogen on a neighboring molecule. So we meet the definition, so we know we have hydrogen bonding. When I look at ion dipole forces, I got 2 problems there. One, I only have 1 substance. Remember, ion dipole, we must have 2 substances. And 2, there are no ions here. I don't have any sodium ions or chloride ions. This is a partial positive, partial negative, which is not the same. And so what I see is we're not going to see any ion dipole forces or any ionic forces in this molecule. Right, another example here. Hopefully you recognize this functional group. This is an ester. And what I want to look at here is first, do I have dispersion forces? And I can say, yep, there are dispersion forces because it doesn't matter what I'm talking about. I always have dispersion forces. It's just for nonpolar molecules, that's the strongest type of intermolecular force we see. On that list where we looked at, we started with dispersion forces and went to dipole-dipole, hydrogen bonding, ion dipole, and ionic attractions. That kind of goes in order from weakest to strongest forces happening. So we know we have dispersion forces. I also see that I have some oxygens present, which is probably going to indicate that this molecule is polar. And so because it's polar, I'm going to deal with our dipole-dipole forces. Okay. Now I have to decide if I have hydrogen bonding. And so what I want to look at is where my hydrogens are in this molecule. So what we're going to do is say, okay, we've got hydrogen, hydrogen, hydrogen. Okay. No hydrogens on our oxygen, no hydrogens here because we've already got 4 bonds. Hydrogen, hydrogen, and hydrogen. And what we see is that we don't actually meet that definition of hydrogen bonding because we have to have a hydrogen attached to a fluorine, oxygen, or nitrogen and attracted to the fluorine, oxygen, or nitrogen on a neighboring molecule. And because we don't have that, we actually don't have hydrogen bonding. Just the presence of hydrogens is not going to get us to hydrogen bonding. And we don't have an ion, so that means we don't have ion dipole forces, nor do we have ionic attractions. Here's another example here. This is actually a triethylamine is the name of this molecule. And what we want to look for again is what characteristics do we see in this molecule that are going to help us see if we in fact have a polar or nonpolar molecule. I'm actually going to go ahead and draw in these last two lone pairs. There's actually a lone pair of electrons there on that nitrogen in the middle. So when I look at this again, I know I have dispersion forces because everybody has dispersion forces. When I look at this, that presence of the nitrogen is a good clue that we're dealing with a polar molecule. So this is kind of like what we talked about in class on Wednesday when we looked at having three groups around it and have that one lone pair. We would have a polar molecule because basically that team in our tug of war game walked away, and so somebody's going to win that game. And so we have a polar molecule, and so that means we can have dipole forces. Now, in order to have hydrogen bonding, we would have to have a hydrogen attached to our nitrogen right here, but we don't have that. We have three ethyl groups, these carbon groups, R groups attached to the nitrogen, and we have a lone pair. We're not going to see four bonds around nitrogen, so we can't say there's an implied hydrogen there. So we don't have a hydrogen there, therefore we do not see hydrogen bonding. We also don't see ion dipole or ionic forces because, again, there are no ions present. So what we want to look at here is the difference between solid, liquid, and gas and how those properties kind of are determined by those intermolecular attractions. So when we look at substances in the gas phase, what we see is that those atoms are super far apart from one another. And in fact, this picture does not do justice. If we were to draw this to scale, what we would see is that we could have one gas molecule in this box and the rest of it will be empty because the distance between those molecules is so huge relative to the size of those molecules. So when we look at gas molecules, we know they're very far apart from one another. They're not interacting with one another. They are colliding, but they're not interacting with one another. And so as a result, we see very little, very weak, if any, intermolecular forces because these molecules are so far apart, or particles are so far apart from one another. When we go to something in the liquid phase, what we start to see is that we have stronger intermolecular forces, okay? Because now there's attractive forces that are pulling these molecules closer and closer to one another to get them to stay in a liquid phase, because in order to be a liquid, those molecules have to be really close together compared to our gas. And even more so when we get to a solid, we have even stronger intermolecular forces. And so now we can see how these properties help us predict what phase something is going to be in. So if I look at something like helium atoms or even hydrogen molecules, what I see is that hydrogen, for example, is nonpolar, has very few electrons, so it has very weak dispersion forces, and it is in fact a gas at room temperature. And we'll see this for a lot of our substances when we look at hydrogen, H2, N2, O2, F2. All of these substances have very weak intermolecular forces and therefore are gases at room temperature. For other substances, say water, which actually has fairly strong intermolecular forces because it has that hydrogen bonding in there, what we see is that it's a liquid at room temperature because of those intermolecular forces. So understanding intermolecular forces helps us understand why substances behave the way they do and why they're in the state that they are in. So just like intermolecular forces affect the properties of substances in terms of their gas, liquid, or solid, we also see that they affect things like melting point and boiling point, because really these are kind of governed by the same properties. So if I look at a molecule such as, let's look at propane. Okay, so there's propane where we just have three carbons, so we'd have CH3, CH2, CH3. What we see is that propane is nonpolar. All it has are those dispersion forces. Okay. And what we're going to see is that its boiling point, which is the point where it goes from liquid to gas, okay, it's not a set temperature. It differs depending on the substance and the pressure, but it's the temperature at which something goes from liquid to gas. That's the boiling point. And what we see is that we only have dispersion forces compared to something like propanol, so adding an OH there on the end. Now we have dispersion, dipole forces, and we have hydrogen bonding. And so because our intermolecular forces are much stronger, what we see is that the boiling point of propanol is actually much higher than our propane. Now, a common misconception is that boiling one always has to be hot, and that's so not the case. Boiling is when we go from liquid to gas, and that's the only thing that defines it. We can actually boil water at room temperature. What we have to do is lower the pressure. Now, we know that the boiling point of water at 1 atmosphere, so at 1 atm, which is standard pressure, is 100 degrees Celsius or 212 degrees Fahrenheit. But that's only at 1 atmosphere. If we lower the pressure, so lower the atmospheric pressure, say putting it under a vacuum, we will have a lower boiling point. So whenever we're looking at properties of substances, we can't say it's a fixed temperature. We have to know at what pressure it was determined. And boiling point is going to happen for different substances at different temperatures. If we look at liquid nitrogen, okay, so liquid nitrogen, what we see is it actually boils at 77 Kelvin. Okay, so 77 Kelvin, about 200 degrees Celsius below zero, is where that, so it's minus 196 degrees Celsius. So nitrogen actually boils at that temperature. So boiling doesn't necessarily mean hot. It's the temperature at which something is changing from liquid to the gas. And that's what we're worried about for that definition. Now, as we saw in the previous slide, what we can tell is that the stronger the intermolecular forces are, the higher the boiling point is. So we looked at the example with propane and propanol. We could do it with a variety of compounds. We see that water, H2O, has hydrogen bonding, has a fairly high boiling point. It's a liquid at room temperature and pressure, compared to H2S, which does not have hydrogen bonding because it doesn't meet our definition of a hydrogen attached to a fluorine, oxygen, or nitrogen. So no hydrogen bonding. And at room temperature and pressure, H2S is actually in gas phase because it is a much lower boiling point, because what we see is that the forces holding those molecules together are much weaker, and as a result, it doesn't take as much energy, as much heat, as much input in order to break those molecules from the liquid phase to the gas phase. For water, which has much stronger intermolecular forces due to that hydrogen bonding, it takes more energy to break those molecules apart from one another, to separate them from the liquid phase into the gas phase, and as a result, we have to put more energy and we have to heat it to a higher temperature to get enough energy to actually boil that water, to break those intermolecular attractions and move those molecules apart from one another. So let's look at some examples here of trying to kind of rank these with the highest boiling point. Remember, the substance with the highest boiling point is going to have the strongest intermolecular forces. So highest BP has strongest intermolecular forces. So we're going to abbreviate that IMFs there. So strongest intermolecular forces. So I'm first going to divide this up in kind of two little sets here. I see that in the first two, up here at the top, I just have dispersion forces because I don't have any polarity, no dipole-dipole forces, no hydrogen bonding, nothing, just dispersion forces. Down here at the bottom, I see that both of these will have dipole-dipole forces, and both of them will have hydrogen bonding. But I need to be able to distinguish between the two of these. One of them does have a higher boiling point than the other. And so now I know that their dipole forces are going to be about the same strength because they have the same OH group. Their hydrogen bonding strength is going to be about the same. So what I actually go back to is their dispersion forces. Remember that we said dispersion forces result from the presence of electrons. From presence of electrons. And so what I want to look for is say, well, which one has more electrons? Well, the one that has more atoms is going to have more electrons because we're all looking at the same types of atoms here, carbons and hydrogens. So when I look at this very last one, even though the dipole-dipole forces and the hydrogen bonding for the third and fourth examples here are exactly the same, the dispersion forces are going to be different because this last one is a longer molecule, more atoms, more electrons, stronger dispersion forces. Now there's not going to be a huge difference between these two, but this last one will actually have our highest boiling point. On the other extreme, the lowest boiling point, we can do the same thing. We don't have to worry about dipole-dipole forces or our hydrogen bonding. Here we're just looking at dispersion forces. And when I look at this first one, propane versus butane, I have fewer atoms, fewer electrons, and so this of these four will have the lowest boiling point. Now, notice that we weren't comparing these to some absolute value. I wasn't saying, was the boiling point going to be greater than or less than 52? Okay, I can't do that from this type of analysis. All I can do is compare two substances and say, okay, this one has stronger intermolecular forces than this one. It's all relative or ranking compounds in order of increasing boiling points or decreasing boiling points, because we're really ranking them in order of increasing strength of intermolecular forces or decreasing strength of intermolecular forces. So it's not about comparing them to some specific value. And I can't say, oh, well, of course, propane's going to boil at some certain temperature just because of this. It just has dispersion forces. I can only look at these compounds in comparison relative to one another. So I also mentioned this in class on Wednesday. Solubility depends on polarity, so that like dissolves like. What we're looking at is that polar substances are soluble in polar solvents, nonpolar substances are soluble in nonpolar solvents. And then this gets back to those intermolecular forces, those intermolecular attractions. If I have a substance like water, okay, where I know I have my dispersion, and I have all these dipole-dipole forces, I got some hydrogen bonding, okay, and I compare that to, say, butane, where I really just have dispersion forces, there's nothing really there in the water molecule that can really interact with the butane molecule and vice versa. So these are not going to interact with one another. They're not going to be soluble in one another. Water wants to look for something that has similar properties to water. So if I looked at something like methanol, well, these two would mix great together, because what I notice is that water has dispersion forces, dipole-dipole forces, and hydrogen bonding. Methanol has dispersion forces, dipole-dipole forces, and hydrogen bonding. So these two are going to be well mixed together because they have similar intermolecular forces. Neither one of these two compounds are going to want to react with butane, because butane doesn't have the same properties that they do. So this is where that expression like dissolves like comes in. It's all about the polarity of the molecules. And we gave the example in class of water and oil, or vinegar and oil, like for salad dressings. Well, you can shake it up and kind of force it to intermingle, but you're really not mixing them together, because as soon as you let that sit for a couple of minutes, what you're going to see is the layers of the vinegar and oil separate from one another. So here we look at some examples of which compounds are more soluble in water or in oil. And everything comes back to the polarity and the intermolecular forces. What I see is that water is polar, oil is nonpolar. So substances that are polar are going to be better dissolved in water. Substances that are nonpolar are going to be better dissolved in oil. So I look at my CH3OH and I see I've got that oxygen in there. That's a really good clue that I'm dealing with a polar compound. And so as a result, it's going to be best dissolved in water. When I look at C6H6, that is going to be nonpolar, okay? There's just carbons and hydrogens, and so as a result, I don't see anything but dispersion forces, so that's going to be better off in oil. KCl is actually ionic. Now we can see interactions between ionic and polar compounds because they both have those kind of significant charge separations. One, the KCl in this case, much more extreme, but we can still see that ionic compounds can dissolve in water because the difference in charge in polar compounds is similar enough to that difference in charge of the ionic compounds. And we saw in the previous slide how kind of those water molecules would actually surround that sodium ion. They'll actually, or in this case, the potassium ion, they would also do the same to the chloride or the anion. So they can kind of surround that because of those partial negatives and partial positives. When I look at this last example, I see a big, long hydrocarbon. And so that is screaming to me non-polar molecule. And so that's going to be better dissolved in oil. So everything we're talking about this whole lecture is actually looking at those intermolecular forces and looking at that whole issue of polarity that we talked about in class on Wednesday, because that really drives all of these properties and so much of chemical behavior and the way substances interact with one another, without not talking about chemical reactions, but actually like interactions with one another, are actually predicted based on those intermolecular forces, which are based on polarity. And we'll see the same thing happening when we look at um, when you look at DNA, you'll start to see these intermolecular attractions again, looking at proteins and enzymes and how they fold and kind of form these superstructures. It all has to come back to these intermolecular attractions and determining whether parts of the molecule are polar or nonpolar. Now, up until this point, we've kind of looked at the whole molecule and said, well, the molecule is either polar or nonpolar. However, when we start looking at some biological molecules, what we see is that they get very large, and so they can have different regions of the molecule that behave slightly differently. And so what we have here is something called amphipathic molecules. And what it is that they contain both a polar region. In this case, it's this carboxylic acid head. This is actually a fatty acid molecule. It's got a carboxylic acid head here on one end, and we have this nonpolar region, which is just this hydrocarbon chain. Now, if I'm looking at something like acetic acid, which is a very small carboxylic acid, in fact, it only has 2 carbons there, then I just say, well, this molecule is polar. I don't have to worry about it having a polar or nonpolar region because it's so small. The whole thing is polar. It only becomes an issue when we look at these very large molecules. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, and many of our fatty acids are much longer. If you look at like stearic acid, which is found in red meat, it's got 18 carbons. There are longer ones than that. And that's when we really have to worry about this region, because now the molecules are so huge that the way they're interacting with other molecules is going to depend on which part of the molecule you're talking about. It's so big that one end basically can't control the other end. And so we'll start to see some of these interactions happening. But the thing we look at is amphipathic. So some molecules have 2 separate parts, okay? And there's no clear cutoff as to say, okay, well, when does it stop becoming a polar molecule like acetic acid to where we start having to worry about having a polar and a nonpolar region? Just like everything else, just like we looked at the polarity issue, we talked about the comparison to a rainbow about where red ends and orange begins. It's the same thing here. You can find tables that say, okay, well, after 5 carbons it matters, or after 6 carbons. I'm not worried about any specific cutoff, but knowing that after we get a larger molecule. When I look at, say, comparing, again, doing a comparison, looking at these 2 molecules, I could say, well, yep, acetic acid, I can just call that polar. But when I start looking at something this big, then I have to worry about these 2 regions. So when we're getting to 8, 10, 12 carbon atoms, these big, long fatty acids, then I'm going to worry about the 2 different regions on that molecule. So that's it on this unit's material. Next week, when we have our group activity, I'm assuming classes will be meeting on Monday and Tuesday, but when we have our group activity, what we'll actually be doing is kind of going through this some more, looking at some molecules, having you practice this and try this on your own to be able to determine whether we have polar or nonpolar molecules, what we can see about trends and boiling point, and also looking a little bit at the fatty acids and the triglycerides. And there's actually a video on Sapling for you to watch about the triglycerides, which are the kind of how the fats are stored in our bodies when we look at those triacylglycerols or triglycerides. So make sure you check out that video as well. So that's what we're doing in the groups on Monday and Tuesday. On Wednesday, we will be having basically a help session. You can post questions on Piazza or bring questions with you to class. On Monday, I will post a note on Piazza, so you can just post your follow-up questions to that, because I'll just simply print that page. If that doesn't appear by, say, Monday afternoon, if somebody can send me an email to remind me, that will be great. It just means I've forgotten to do that, but I'll post that up so you can post your questions there. And then on Thursday is our exam. So next week you'll see a seating chart. Just like before, we will be seated in Memorial Hall. I believe that we still have the room reservation for the nursing building, so we'll confirm that as well. If you need to change, so if you had a broken computer and were nursing last time and now you want to be in Memorial, or your device has broken or something's the matter and you don't want to be in Memorial, you want to be in the College of Nursing computer lab with those devices, you need to please let me know. Send me an email that says 103 exam 2 seating in the subject line, big bold cap letters on the subject to make sure I see that so that I can move you to the correct spot. There will be a new seating chart. You will be assigned a new seat in Memorial Hall. Okay. As always, if you have any questions, please let me know. Again, I'll be monitoring Piazza this weekend to answer questions as they come up. Have a great weekend. Please be careful, stay warm. If you do go out, bundle up. It's going to be cold and the wind chills are going to be pretty rough. So, whole weekend to just snuggle up with your chemistry book. So, anyway, I will see you on Monday morning. Have a good weekend.